Welcome everyone. I'm Mingxi Wu, head of engineering from TigerGraph. TigerGraph is the most scalable enterprise graph database in the cloud and on your prem. And here's today's agenda. I first motivate people why you need a graph for your data lake. And after that, I will talk about why TigerGraph is investing on building a cloud-native graph database in the cloud. And also, after that, I will unveil the new latest cloud-native graph database, codenamed GraphHouse. And I will also cover the upper trend lately, graph-based rack. And in the end, I will show a demo of our GraphHouse. So why you need a graph for your data lake? And we know that the data is in a movement to the cloud, and it largely benefits from the object storage technology. You can really dump everything in S3 or Google GCP buckets or Azure object storage, and it has unlimited storage capacity and have unlimited I/O bandwidth due to the replication of your data blocks. And people are piling up their data into data lake. And naturally, you have different departments, have different team trying to ETL their data and store them in data lake. And you have data silos. And due to the multiple pipelines and at varied velocities to power your data into data lake. And also the heterogeneity come in different formats. You have structured relational tables, you have semi-structured JSON file, XML files, and you even have more and more unstructured multimedia data, such as documents, images, and videos stream that pile up on your object store. And since different data have basically describing the activities or the characteristics of your objects, and you have inherent redundancy. So I see pricing needs for people to ETL their data and integrate the data silos into a workable format so that it drive the most insightful data insights for your business needs. And you can argue that the DBT, you can use DBT, the popular open source tool, to use different relational drawing operators to ETL your data from heterogeneous data sources. But I would argue a graph is actually a natural integrator for your data elements in the cloud. And why I say that? Because graph use node and edges to represent data. It has a unified form. And the graph model using node and edges is the natural representation of the real world relationship between objects. And when you ingest your data into a graph database, it naturally deduplicates your data elements at ingestion time. And also the graph schema evolvement is really flexible. You can imagine your graph is a tree, and prune a branch or add a branch into the tree does not shake the global structure of the graph. So your existing query workloads will not get affected. So it's really flexible. And the second reason that you need a graph for your data lake is really having an advantage in providing performant queries. And we know that in the cloud, you basically have three forms of compute engine. And the first is the incumbent relational database management system. And it uses joins to connect your data elements at runtime. And everyone knows that drawing has limitations. When you join hundreds table, not even thousands, you will experience the explosive drawing intermediate results problem. And people start materializing drawings to trying to eliminate this drawing bottleneck. And the second compute engine you can find in the cloud is key value store, like MongoDB or some other key value database. And its underlying primitive is put and get. And this is really benefits for those online serving, as serving or online retrieval of information very quickly. But it's not good for connecting data, and it's not good for doing any complex analytic queries. And the third category is MapReduce. And MapReduce compute engine is really flexible, and user can program any user-defined function into the mapper and the reducer to do any ad hoc computing. But it doesn't eliminate the need for runtime join. So it has the same limitation of relation database runtime join. And graph database is really emerging as a third canonical database category due to its unique advantage of graph database format. And the graph native storage format, as I said, you can think as connecting the dots at ingestion time. And in the computer science term, it's used adjacent list to represent vertices and edges. And everything is connected in their necessary form during one pass of your data at the data ingestion time. At runtime, you just traverse the graph storage from the starting vertices, and you don't need to do a Cartesian join with other siloed data tables. And due to this native graph storage format, if you design your architecture well, you can explore the multi-core compute resource to do really fast performant query processing at runtime. And the third advantage of using graph for your vast data lake is graph query language is really Turing complete. It can cover SQL query language expressivity. And it can also go beyond that and doing any ad hoc feature engineering and doing any ad hoc graph algorithms to do unsupervised mining of your data. And any programming logic can be done in graph query language. I will elaborate this more in the following slides. And also graph, due to its similarity or closeness representation of the real world, and it can model and present the query results as vertices and edges. And this is very closely to what we perceive the world. And also where UI, you can really interact with your data by point and click and explore and discover while you're thinking about you or reasoning about your data sets. And it naturally enhances your explainability because the visual representation really is a digital twin of your physical world. And you can really make close reasoning and explain what is happening in your data. And TigerGraph has been existed more than 10 years, a decade. And we have seen the world is really full of graph-driven data problems. And I listed the top 3 that we observe in our customers. The first and foremost is the financial crime. And the crime can happen in banking transactions, account transfer money, and for money laundering and for fraud detection. We really see that the accounts can reach variable length to the target victims, and you really don't have a fixed length of your path. And a graph can really help you to solve this connecting the dots problem. And the second popular graph-shaped problem is called agile operation. So imagine you build a car. You really have thousands of parts underneath the car product. And if you see a surge in your car demand and you want to find where your parts supplier have enough stocking to supply you market demands, you want real-time decision, and you want to connect the dependency of your parts to make the car into different suppliers and do real-time query according to this complex supplier network. So we call this kind of complex network and dependency graph and real-time update and real-time query called this kind of problem agile operation. And we see many customers suffering from their relation database existing solutions. And once they switch to graph database, and everything seems so natural and elegantly solved. And the third is customer 360. And we see that customer interact with their vendor in different touch points. And imagine that you are a patient and you want to call insurance company to submit a claim or dispute a claim. And the call center of the insurance company need to quickly see where is the historical touch points that you interact with the insurance company. And that require a really flexible and real-time agile database to look up the data. And the data is really a graph shape, and the graph database can help you to manage your customer 360 of heterogeneity touch point very easily. And the last category that of graph shape data is really the recent AI movement. And we know that the large language model is really a predict model. It's a statistical model that can predict the next token of your word. And more and more people are hesitate to rely on large language model due to the undeterministic of the language model. And one big application trying to illuminate the hallucination of your large language model is use factual data. And the best factual data representation is graph. And I will cover that in the later part of this talk. So seeing the benefits of graph for your data lake, and I want to discuss briefly why we want a cloud native architecture. So traditionally, when people purchase Oracle or any relational database Teradata, and they need to go through a long provision process. They need to contact their IT department and predict their computer capacity and storage capacity. And the IT department will provision those hardware and then ship to the data center and then install the software license. And the market is really dynamic, and people often see a change of their workload and the demand, and they hit compute ceiling due to this setup, run, and then reset up and rerun. This kind of dilemma in enterprise software and compute provisioning to service process. And the data is actually having a trend to move into the cloud. And largely it's due to the uncapped compute architecture in the cloud. And you really no longer need to worry about your compute setup. And you really imagine that you have uncapped compute resource. Even your workload is changing. You are no longer limited by compute capacity and go through the lengthy provisioning step from data center and IT department. And you can run different queries independently on their own compute resource due to the vast compute capacity on the cloud. And the same thing happens for the object storage. And due to the object storage technology, you have a reliable storage in the cloud architecture, and you also have uncapped object storage that you can pile your data on. And it's also secure and geo-replicated to handle disaster recovery, and it's durable. And another big benefit of object storage is having high throughput. The high throughput come from the replica of your objects. And also it has low cost and scale in the planet level. And everything happening in the cloud is cost effective because it's pay for use, and it can auto pause and auto resume when there are no activities and when there are activities picking up. and it can also dynamically adjust it. So people saying that the cloud architecture is really becoming the utility of your daily life, and your data is your assets, and you use the cloud resource to generate value from your assets. And with the motivation of GraphHouse Lakehouse and the motivation of a cloud native architecture for Graph, I'm going to announce the GraphHouse product that latest release from TigerGraph, and it's designed for your data lake, and it's using the cloud native architecture. And I know there are a lot of people have different experience using graph database, and some people say it doesn't promise what the graph database should deliver. I would invite you to switch from those toy departmental graph database to TigerGraph to really see the value of graph native storage format and MPP architecture. So GraphHouse really designed for the cloud architecture with unmatched scalability. And TigerGraph is the only one in the planet that have delivered 103 terabytes data benchmark using the authoritative LDBC benchmark. And no one else can claim this. And TigerGraph have done that with partnership with AMD and using AWS cloud hardware to do this first time in this world. And so far, we are still the only one can deliver at this scale. And this benchmark is really designed 20 very difficult queries to choke your engines. And TigerGraph can finish them in minutes also for each query. And the second advantage of GraphHouse is really can handle HTAP workloads on the graph database. And HTAP means hybrid analytic and transaction workload. And we can handle short query or LTP query. And then we can also handle large scale deep link analytic query, such as PageRank or 6-hop and more traversal of your data elements. And also GraphHouse is secure and reliable. It's using S3 as storage, and it supports backup and restore point in time. You can, if you experience some hiccup, you can restore to your data snapshot anytime in the history. And TigerGraph also provide role-based access control at both schema level and the data graph elements level, vertices and edge level. And everything happened in TigerGraph Cloud is tracked by auditing log, so that you can trace log to see what's going on. And also data is naturally encrypted on REST on S3. And here's the picture of how the cloud native architecture look like. On the left is your compute resource, and it's called workspace. You can have one read-write workspace and many read-only workspace attaching to the same database. And database is a storage file on S3, and it has infinite I/O bandwidth for you to spin up different workspaces for compute needs. And I want to clarify that TigerGraph Cloud Native Architecture is having the flexibility for either TigerGraph manage, or you bring your own data plane, and then we call it enterprise VPC configuration, so that you can double secure that data never leave your VPC and well managed remotely by TigerGraph control plane. And here are more highlights of the cloud native GraphDB architecture. And cloud native mainly means separate of storage and compute, so that you can have flexibility to scale your compute independently from your storage. And auto start and auto stop will save your costs on the cloud. And backup and restore point in time allow you to have time travel capability of your data state. And TigerGraph is also have a lot of enterprise readiness features. For example, we summarize our canned solution based on our past customer experiences to help people jumpstart on their vertical application using solving graph-shaped problem. And RBAC has mentioned, and encryption on S3 is mentioned. And BYOC means bring your own cloud, bring your own data plane to TigerGraph, and so that your data is residing behind your VPC, while TigerGraph is managing for you to provision and upgrade the system. And Graph database emerged as a good database for AI and ML workload. And TigerGraph will support vector operation natively, and GCQ will query vector attributes and doing top K or range query to combining your structured data and unstructured data into the same workload. And also we will provide GraphDB-based RAG solutions. And out of the box, you can see your data statistics and insights. And this is pre-computed during the ingestion time. And also we have auto mapping to help you integrate your data silos during data ingestion time. And there are easy of use. I will leave to the demo time, and easy of admin, I will also leave that into the demo time. And before I show the demo, I will talk about graph-based RAG. This is what we see. So as I said, large language model is a statistical model. It really have billions parameters to help you to predict what are the answer for your questions, natural language questions. But the drawback is it's statistical and it's non-repeatable and non-explainable. And it's trained by vast data at a large scale. It can incorporate every nuances and main branches from your past knowledge, but it's only a predictable model. And in order to enhance the usability of large language model, you really want a factual database to help you to eliminate that hallucination. And factual database can be any form, and I think a graph is very competitive in doing the RAG-based application for large language model. And it's explainable, can be repeatable, and it's deterministic. And it can bring your organization taxonomy in the graph to help you to do real-time lookup of your information. So here's a diagram of how you use TigerGraph to do a knowledge graph builder. So basically, you have your knowledge graph information. Outside, you can put ingest into TigerGraph and build your intelligent knowledge graph. And this intelligent knowledge graph can incorporate your documents, your Delta documents, and also taxonomy of your domain knowledge. And also, you can pile in other operational data like time series into this graph. Everything can be heterogeneously integrated into a knowledge graph. And at runtime, people use chatbots to ask questions. And under the hood, the orchestration layer will interact with large language model and then interact with TigerGraph intelligent knowledge graph, provide contextual information to the large language model, and large language model can use the contextual information to answer your questions and in a more deterministic way. And besides the RAG, TigerGraph also provide a set of library for your out-of-box doing graph algorithm. And here's a quick look and feel of GraphHouse. And you organize your cloud resource in work group. And each work group is composed by compute resource called workspace and storage resource called database. And this is your work group 1, project 1. And under this work group, you have 3 compute cluster, A1, A2, and A3. They can have different sizes. And all of them are attaching to the same database A. which is the S3 files. And then you have another database B that attached by two compute cluster, B1 and B2. And together they are your project one work group resource. So with all the introduction, now I'm going to play a demo.
Mingxi, before you play the demo, maybe you can answer 1-2 questions.
Yeah.
Yeah, one question related to your earlier showing the vector storage status. Native vector supports would allow cosine similarity sort of a search, or do your graph, what kind of search you have?
Let me see. So the question is about the vector search?
Yeah, so like a native vector support would allow cosine similarity sort of search. That's the question.
Okay. Yeah. So here, so TigerGraph actually, so like any database, you can extend your record with vector attributes, and then you can do top case search using similarity score, or you can do range search by providing a query vector and then providing a cutoff. And then your query vector will go through your data elements and then find all the data elements that has a vector within the cutoff range of the query vector. So TigerGraph will provide two predicates. One is called top K predicates, one is range predicates with a cutoff. So it's covering all the vector search capability. You can think in the worst case, you can use TigerGraph as a vector database. In the degenerate case, yeah.
Sure, thanks.
In the more complex case, you can use pre-filtering to find the relevant vertices. And then within the filtered vertices, you want to do similarity search and range search. Yeah.
Awesome, thanks.
So
all this will be in the GCQ query language. You don't have to switch back and forth between vector search versus graph query language.
So one follow-up question is in the normal vector database, especially what you store is embeddings. What do you have here? Is it embeddings or is just the actual?
Yeah, so we will store the embedding as additional attributes for our vertex.
I see.
Yeah.
Cool. Thank you.
Okay, now I'm going to play the demo.
Today, we're excited to introduce TigerGraph Cloud 4, a brand new platform that makes graph analytics on the cloud easier than ever. With the innovative separation of storage and compute,
looks like we are not seeing the right
ensures you get the best performance and cost efficient into some of the groundbreaking features of TigerGraph.
We can see your demo. We are just seeing you.
Let's start by creating the first work group. A work group is a logical collection of compute resources and database storage. It helps. Today, we're excited to introduce
Just 1 second. I'm trying to reshare.
Yeah, we only see we hear the audio, but I don't see the video.
Graph Cloud 4.
Can you see?
A brand new platform that makes graph analytics on the cloud easier than ever. With the innovative separation of storage and compute, TigerGraph Cloud 4 ensures you get the best performance and cost efficiency tailored to your needs. Let's dive into some of the groundbreaking features of TigerGraph Cloud 4. To begin, let's start by creating the first work group. A work group is a logical collection of compute resources and database storage. It helps you organize and manage your resources efficiently. Enter a name for your work group, for example, Demo Work Group. Then select the region where you want to put your resources, such as US East. Then click Next. Give your workspace a name, for example, Read-Write. Then select the TigerGraph version you want your workspace to run on, such as 4.1 Preview. In the Workspace Details panel, you can select the compute resource size that suits your needs. TigerGraph Cloud 4 offers auto-suspend and auto-resume options. This feature automatically puts a compute instance to sleep when it's not actively working and reactivates a previously suspended workspace when there is traffic. Let's enable auto-suspend and set the suspension time to 60 minutes. Then enable auto resume. You can then choose to create a brand new database, which will set your workspace to read-write mode, or attach to an existing database, which will set your workspace to read-only mode. You can also enhance the capabilities of your workspace with add-ons. These add-ons enrich what TigerGraph Cloud can do, making your work more efficient. In addition, TigerGraph Cloud offers a variety of prepackaged solutions tailored to address common business needs and use cases. These solutions include predefined schemas, loading jobs, and sample data, allowing you to begin exploring and analyzing your data right away. You can quickly get started with these solutions during workspace creation or add them at any time afterward. Once you are done, click the Create button. This process typically takes a few minutes for the workspace to become ready. Let's fast forward to skip the waiting time. Congratulations! You've successfully created your first workspace. Now let's set up the graph schema for your workspace. You have a few options to create a graph schema. If you're comfortable writing GSQL queries, you can create the schema directly with the new GSQL editor. Designed with user convenience in mind, the GSQL editor offers a user-friendly interface that simplifies the process of writing, testing, and optimizing GSQL queries. With syntax highlighting, code completion, query execution, and debugging capabilities, users can easily develop and fine-tune their graph queries. Additionally, the GSQL editor enables seamless collaboration within organizations by allowing users to share GSQL files, fostering teamwork and facilitating efficient collaboration among colleagues. Alternatively, you can use the Schema Designer, which offers an intuitive interface to design and visualize your graph schema. The Schema Designer allows you to easily drag and drop elements, define relationships, and instantly see how your schema will look. This visual approach simplifies the process, making it accessible even if you're not familiar with GSQL. If you have data that you want to be loaded, you can design the schema while mapping your data to TigerGraph. TigerGraph provides a flexible and powerful data loading feature that allows you to ingest data from multiple sources into your graph database. This capability is essential for building comprehensive and connected data sets that can drive insightful graph analytics. Whether your data resides locally or in the cloud, TigerGraph makes it easy to map, transform, and load your data efficiently. Let's first try to load your data from local files. Simply drag and drop the files you want to load into the panel. After all the files have been uploaded to the server, click the Next button to configure the files. You can adjust the separators, end-of-line characters, quotes, and headers for each file. Once the configuration is complete, click the Next button again to set up the mappings. In this step, you can configure how your data is mapped to the graph. Click on any vertex or edge where you want to load your data and select the source file. Use the Quick Mapping button to either automatically match all corresponding attributes from the source to the target or create new attributes if no matches are found. Repeat the same process for the nose edge. In the mapping, you will need to select the From person ID and the To person ID from the source file. Click the Next button to continue. In the final review and confirmation step, once you are satisfied with the changes, click the Confirm button to proceed with the loading. You can also load data from an S3 bucket. This method enables you to load large files into TigerGraph without uploading them directly to the TigerGraph server. Simply provide the credentials for your S3 bucket, including the access key and secret key, and then add the file URI individually. Similar to loading from a local file, you can review the settings before configuring the mappings. This time, let's load the data for the post vertex, as well as the has creator and likes edges. Simply select the desired vertex or edge and the file you want to load the data from, using the Quick Map button to align directly with the predefined schema. Repeat this process for the has creator and likes edges, ensuring that the from and to vertices are correctly mapped. Click the Next button to review your mapping and confirm the loading. Furthermore, TigerGraph supports loading data from Datalake. Simply select Datalake as the source type, then click the Open in GSQL Editor button. TigerGraph Cloud will generate the relevant GSQL template to guide you through the loading process. Unlike the pull model used for other sources, The TigerGraph Spark connector leverages the DDL endpoint to utilize a push model for data transfer. This approach requires a predefined loading job to process the data frame. The connector supports both batch and streaming writes, allowing for flexible and efficient data integration. We've set up a loading job called load comment that maps the columns from the source delta table to vertex attributes. In Spark, you can use this template to write both batch and streaming code. Just include all the necessary writer options like the TigerGraph Cloud endpoint URL, the graph name, the secret, and the load job name. Let's start with the batch write. According to the log, 466,076 rows have been successfully loaded. Alternatively, you can set up a streaming write from Datalake. To do this, you will need to configure the Datalake change data feed and the write stream to transfer delta table changes to TigerGraph. This setup not only tracks newly appended data, but also updates to the existing data. The TigerGraph Spark connector also supports reading data from TigerGraph. For instance, we can query vertices of type comment using operators such as select, limit, and sort. Let's execute this query and examine the resulting data frame. Additionally, the connector supports running pre-installed GSQL queries. Here we have the page rank query already installed. We'll run this query in Spark for the person, vertex, and the nose edge. The results will include the vertex ID and its page rank score, sorted by the score. In addition to data loading, TigerGraph Cloud integrates with prepackaged solution kits. These production-ready solutions include predefined schemas, loading jobs, and sample data tailored for various use cases. You can select these solution kits when provisioning a new workspace or add them to an existing workspace. Simply give your solution a name and select the workspace where you want to install it. Then you have the option to load the sample file, map from your own files, or start with blank data and load it later. Let's choose the sample data option and proceed with the confirmation. You can also review the solution graph schema before installing the solution. Initializing a solution typically takes a couple of minutes, including creating the schema, loading data, and installing queries. Let's fast forward until the solution is fully initialized. Once your solution is created, you can use the built-in Insights applications to view the data. These applications provide a user-friendly interface for exploring and analyzing the data, allowing you to gain valuable insights and make informed decisions based on the graph data. You can also use the new data profile feature on TigerGraph Cloud to view and analyze your data. This feature leverages advanced algorithms to analyze the graph data, calculate data distribution, and identify meaningful patterns, relationships, and insights. It helps users discover valuable information within their data, even if they are not familiar with the underlying data structure or query language. Another way to search and visualize your graph is through the Explore Graph feature. This no-code interface allows users to interactively explore and analyze graph data. You can use the pattern search box to specify the graph pattern and apply filters as needed. If the result set is too large for visualization, Explore Graph imposes a limit on the graph results, which you can adjust in the advanced settings box. Click Search and wait until the result is returned. Explore Graph offers an intuitive force layout for visualizing your graph results. The force layout dynamically positions nodes based on their connections, simulating a physical system where nodes repel each other while edges act like springs, pulling connected nodes together. Additionally, you can apply the PageRank or Louvain algorithms to the retrieve subgraph to quickly gain deeper insights. With PageRank, you can identify the most influential nodes within the subgraph, while the Louvain algorithm helps you detect communities or clusters. You can also execute built-in queries on the Graph Explorer, such as identifying the shortest paths. This capability enhances your ability to navigate and analyze complex graph data efficiently. Moreover, attribute filtering in Explore Graph allows you to refine your data visualization based on specific attributes. It also shows the value distribution for a selected attribute, enabling you to focus on relevant data points and understand the attribute's impact on the overall graph structure. In addition to using Explore Graph, you can also utilize the GSQL editor to query the database. There are two primary methods for querying the database. writing basic G-SQL queries, or using OpenCipher queries. It is recommended to install both G-SQL and OpenCipher queries on the server before executing them. After installing the G-SQL query, you can execute it by using the run query command, followed by the query name and any necessary parameters. Alternatively, you can run the query from the Queries tab. As shown in the result panel, the query results have been populated. Similarly, you can write OpenCipher queries directly in the G-SQL editor. Ensure that the query definition uses the appropriate OpenCipher query keywords. Once the query is installed, let's run it to see the results. The OpenCipher query results are now displayed in the browser. You can also navigate to the Queries tab to view and run all the queries on the server, providing a convenient way to manage and execute your queries. One of the standout features of TigerGraph Cloud 4 is the ability to create a read-only workspace for a selected database. This read-only workspace is essentially a snapshot of the read-write workspace, allowing users to explore and analyze data without the risk of making any changes. Most importantly, it enables users to run OLAP queries without impacting the read-write workspace's OLTP queries. Plus, users can update the snapshot at any time to reflect the latest state of the read-write workspace, ensuring their analysis is always based on the most current data. With our read-only workspace now created, let's dive into running some graph algorithms. We can leverage the built-in algorithm templates available in TigerGraph Cloud to do this. These templates make it easy to apply powerful graph analytics. To see which templates are available for your workspace, simply run show package gdbms algo. Additionally, you can check the details of each subpackage by adding the subpackage name. For example, show package gdbms algo.community. To check the details of a specific template query, run show template query, followed by the template query's full name. Calling graph algorithms is quite straightforward. Simply use the call keyword and follow the parameter definitions provided in our documentation. Since we are running these algorithms in a read-only workspace, ensure that you export the query results to a predefined S3 bucket instead of writing back to the vertex attributes. Let's execute the Louvain algorithm by invoking the template query. The first time you run a template query on a graph, it needs to be installed, which typically takes just a few seconds. After the query is installed, it will take additional time to execute depending on the size of the data. As we can see, the query has been successfully executed, identifying a total of 14 communities. Next, let's execute the PageRank algorithm. Similar to the Louvain algorithm, it will be automatically installed on the server if you are invoking it for the first time. Once the query runs successfully, you can check the PageRank results in the output panel and the file in the S3 bucket. Last but not least, with the latest updates, TigerGraph Cloud now offers enhanced monitoring and debugging capabilities. Users can benefit from detailed metrics and logs, providing deeper insights into system performance and query execution. The real-time dashboard provides a comprehensive view of your system's performance. It offers live metrics on various aspects of your graph database, such as query performance, resource utilization, and system health. You can monitor CPU and memory usage, disk I/O, and network traffic in real time, allowing you to quickly identify and address any performance bottlenecks. The dashboard also includes visualizations for query execution times and throughput, helping you to optimize your queries and ensure efficient data processing. At the same time, the audit log is essential for ensuring security and compliance. It documents all major activities within the TigerGraph environment, such as resource management, GSQL operations, and changes to add-ons and solution configurations. Each log entry provides comprehensive details, including the timestamp, user ID, action taken, and the resources impacted. This detailed information enables administrators to monitor user actions, identify suspicious behavior, and uphold a secure and compliant environment.
Yeah, I think that concludes my talk. Thank you.
Thank you very much. Very impressive I think we're run out of time, so maybe we can have one questions if there's from the audience, if anybody has a question. You can post on the chat if, or you can just unmute yourself if we want to quickly get your question. If not, that's a thanks, Mingxi. It's a great talk and a very impressive product, frankly. So thank you so much.
Thank you.
So our next talk will be Joe from Nvidia. He's going to talk about how to scale the graph neural net with a lot of GPUs.
I see the Zoom has a countdown of 8 minutes.
Really?
Yeah, on the top right.
I'm not quite sure. We have scheduled a 1.5 hour, so it should be another 45 minutes, 40 minutes or so.
Okay, I can go pretty fast. It'll take me about 25 minutes to get through the slides, I think.
It's okay. Let's go through it. So
okay. Yeah, I'm gonna talk about graph neural networks, which is a way to extract really useful these embeddings for vector databases that are popular now. How do you get them, right? That's the question that I'm going to try to answer. So why do we care about graph neural networks? Well, graphs are a natural representation for the world. I think Mingxi did a great job convincing everyone of that. We use them for social networks. We use them for computer networks. We use them to represent molecules, proteins. We use them to represent products in a catalog. We use them to represent transactions in banks and credit card systems. So these come up all over the place. Everyone's life is touched by this. What's not obvious is how do we sort through all these different types of relationships and patterns that occur in these relationships and deal with the massive amount of data that we have. One of the answers that data scientists have come up with are these dense embedding vector representations. We want to get a nice vector, dense vector that captures the complexity in the sparse graph. That's the idea. It's not easy to do. Oftentimes you have to do a lot of compute to get these vectors to be accurate and useful, but that's what graph neural networks are exactly good at. So I'm going to talk about how do we scale these up to the largest graphs in the world and take advantage of that data hiding in the graph. I mentioned, everyone is touched by this. If you use images, photographs can be tracked as graphs, text can be tracked as graphs, molecules, computer networks, everything out there that we do in a modern society on the internet. The internet itself is tracked as a graph. So it's really ubiquitous and impossible to get away from. But how do we keep up? The challenge today is graph data is exploding and growing very quickly. And our customers, Nvidia's customers, are telling us that they're having a hard time dealing with the scale of the graphs that their business provides. And it's not hard to get there. You can get there several different ways. If you imagine a social network graph with 8 billion people in the world and 125 or 8 billion people, 200 friends for everybody, that's a 1.6 trillion relationships in that graph. If you have electronic payments, you can have 8 billion people again, 100 transactions a month, you get to about 1 trillion transactions a month. And this is not hard to find cases of this out there. They're exploding. Every day we see more and more people with trillion edge graphs. And the classic example that started a lot of interest in the financial case is the Bitcoin network. This is a paper written in 2015. This image appears in that paper. This was 125,000 transactions a day in 2015. There's about 400,000 transactions on that network today, per day. But even back in 2015, it was obvious what kind of patterns occurred in these transaction graphs. And by analyzing the graph, you can see these things jump out. You can find the whales, the big single users, the people with large volumes, and many people transacting with them at large volumes. The PageRank score the big dots in this graph are the people who influence the graph the most. So community detection, Louvain is an algorithm that helps you detect communities in graphs. And these are all really important patterns that occur in transactions. And the same things occur in social networks. The same things occur in product catalogs. These are all captured in a property graph model. So the best fit for the world, I claim, are these kind of knowledge graphs or property graphs, where each entity has a set of properties, each relationship has maybe a different set of properties, and you can have an arbitrary number of relationships in the graph. So cuGraph is our Nvidia's package for storing and analyzing very large property graph data sets. This is an open source package, part of Rapids, part of our data science toolkit that we are shipping now with GPUs. And cuGraph is the graph component that has been worked on since the very beginning. I was the one who started the cuGraph work. We now can scale from a laptop or a single GPU or to a giant supercomputer with thousands of GPUs. And we can analyze graphs at the scale of 4 trillion edges for PageRank or Louvain. And we can analyze them. We demonstrated GNN training at that same scale. I'm going to talk about that in a few more minutes. But basically, we can handle the world's largest graphs with open software package, and we can deal with it in time to use it in other workflows. So we're not a database. Well, all we do is take data and analyze it, compute these interesting features from that data very quickly using GPUs. And we have a lot of options. So these are all the algorithms that we support. You can see all the dark green algorithms on the right are ones that we support at these MNMG, multi-node, multi-GPU scale, up to thousands of GPUs. The features on the integration points, cuGraph as a Python package, PyLibcuGraph as a C API or as a C++ API. We have MTMG as a C++ layer for connecting to databases or for connecting to other packages that use high-speed streaming transport. And cuGraph as a service, so as a HTTP service where you can extract features from a graph as a service in another larger internet scale system. When we talk about GNNs, graph neural networks, there's 2 dominant frameworks that kind of are the big fish. Deep Graph Library, DGL, comes from Amazon. They use it extensively internally for their product recommendation, fraud detection systems. And then PyTorch Geometric, PyG, came out of Stanford. And Yuri Leskevec's work at Stanford, he uses it extensively in his work at Kumo.ai. We support both of these with a cuGraph backend to take gigantic graphs and train neural networks using these frameworks. So whichever one you pick, DGL has an advantage in performance at the largest scale. PyG is easier to learn and easier to do research. We support them both. We consider them peers, equal citizens in our world. Go ahead, your mileage may vary, but that's what we're doing. Every GNN, training is not a one-step deal. It's actually a whole workflow you need to go through, starting with data loading from some data source. May it be a database, maybe it's a bunch of local files. It's common to have Parquet files or CSV files to describe your graph. Use extract, transform, and load code, maybe written in Python, maybe written in Java, to construct your actual graph from your raw data. You then enhance your graph with whatever features you think are important, maybe PageRank features, maybe community features, labels for certain detection models like fraud or malware if you're analyzing cyber networks. And finally, you're ready to train. You're actually ready to do some training. The GNN training itself breaks into substages. There's data pre-processing, which is sampling the data, meaning pulling out subgraphs for each node. I want to extract a neighborhood around that node or a sample of the neighborhood around that node, and then training using the standard forward and backward neural network passes we've learned using gradient descent. It turns out the sampling is the dominant work for graphs. It's much more data movement required in the sampling phase than there is in the actual training phase. And we've timed this. We've actually determined the sampling phase, gathering the graph in a distributed graph system is where most of the work is. Once you've gathered the graph, you need to gather the features, the embeddings that you're working on, or features, raw features you start with, say addresses or birthdays or Louvain community features. All of those have to be gathered together before the network can work on it and do the training. And the time spent, there's these little bar charts in the lower left corner. Sampling and gathering features is about 80% of the time. Training only takes 20% of the time. GPUs are really good at training. That's kind of the story. Just gathering the data takes much longer than running the compute needed. It's sparse compute, right? There's a low level of compute per byte as you flow through the graph. So we've tested this on 3 different GNN models, RGCN, GraphSage, very popular, and GAT. GAT and RGAT come up in the MLPerf benchmarks, just recently added to MLPerf. I mentioned service. Basically, this is forced on us. When you're dealing with small graphs, there's no problem. You can just copy the graph to multiple GPUs. You can make replications, no problem at all. Everything is data parallel. It works. But when you run out of memory, when you run out of space on a single node, data parallel no longer works. You have resource contention, you have network congestion, and you have to find other ways. So we've worked out a way to divide the graph up behind the scenes. The user doesn't have to be involved. The user doesn't have to spend time computing how to partition their graph. You just hand us a graph, and cuGraph will handle the distribution across many machines and provide access to it via a client. You can make calls to the client to run analytics, to perform some graph setup, graph filtering, these kind of things. And when you're ready, the graph is in place to do training. And then the training workflow we support is very generic. We allow you to do kind of any data source you want. We allow you to accelerate the pre-processing of that. File I/O is accelerated readers for Parquet, accelerated readers for CSV, JSON. cuGraph sampling is accelerated with special GPU kernels. The data loader is accelerated on PyG and DGL. Finally, the models themselves, of course, use cuDNN and kernels from the CUDA toolkit. And finally, when we write out the embeddings, we can use those and store those embeddings in what we call whole graph or whole memory, which is a distributed feature store, feature vector database that we can distribute across multiple machines to scale up to really big data sets. And that's useful in recommender systems or the final deployment, the fraud detection scheme, whatever method you want to do at the end of the day, these embeddings plug into. It's a pluggable system, and we write out and finally provide those as the input to the next thing. I mentioned whole graph. This is kind of a necessary tool. Distributed key value stores, distributed vector stores are not easy, especially with GPUs. This is the key piece of the system that accelerates the feature gathering I mentioned that takes, one chunk of 80% of the time. And by allowing us to store the data both on host memory and GPU memory, we're able to take much larger data sets on fewer GPUs. This is fully integrated in cuGraph and PyTorch. It works with PyTorch out of the box as a tensor storage also. And we're using this a lot of places, more than we ever thought we would. And I'll show off the big run we did. We used EOS, our internal supercomputer at Nvidia. This has 576 DGX machines running H100 GPUs. There's 4,608 GPUs in the machine, but there's nobody who ever gets access to all of them at once. So we only use 1,024 to do this run. And the run we did was a 1.6 trillion edge graph, starting from a 70 terabyte data set. This is 113 billion nodes in this graph. We used 1,000 GPUs to sample the graph, to build little subgraphs, 1,000 GPUs to train the neural network to produce the embeddings using GraphSage as the model. And this run would take us 20 minutes for sampling and 3 minutes for training. That's for one epoch, to update every node of the 113 billion nodes. We can update it with a new embedding, one epoch of training. It takes about 10 epochs to converge to a final answer, but that's what we can do. And that's very fast for a graph this size. This is probably a world record. Relatively speaking, what can I do with that in the cloud, right? So in the cloud, say I'm on Azure, I can rent GPUs for a certain price per minute I'm paying for. I need about 128 nodes for 23 minutes. The cost to rent a system to do this would be about $668 per epoch, plus storage. I've got to pay for storage in the cloud also. But $668 times 10 for 10 epochs, $6,000 to train a graph of a trillion edge scale is very cheap. I mean, that won't even buy you, one GPU these days, but you can train the entire graph in Azure for that price. What's coming up next? I guess I can pause for some questions or comments, but I'm going to talk about the future a little bit. cuGraph has a long roadmap ahead of it. We're making cuGraph easier to use, to deploy in other ways as a service, as a back end for Network X. We want to have more examples of integration with other frameworks, and better memory utilization. Memory is always short supply on GPUs. We want to overlap the sampling and training as much as possible to shorten that 20 minutes and 3 minutes together, and remove reliance on Dask. So we use Dask to move the data around and shuffle the graph into different machines. That's not needed for the actual GNN training. So we're going to cut that off of the training piece and use just pure MPI, Nickel, Nvidia collectives for that training. And that will cut the time down significantly, we think. I think we can get another 2x about speed up. And you can actually download these functionalities and try them out yourself. We've got containers that integrate the PyTorch, the Rapids ETL processing, the framework for GNN training, cuGraph itself, all the underlying CUDA libraries. We have notebooks that have examples of training different GNNs, and it's all in one container that you can grab for free from Nvidia NGC, the Nvidia catalog of containers, and install it and play with it yourself. Bring your own data is pretty easy to do. You can pull out the test data set from a notebook, plug in your own data set, and start training your own GNNs. Okay, upcoming features, we talked about language models, RAG support for retrieval augmented generation with knowledge graphs, adding all pairs, shortest paths, maximum flow calculations on graphs, supporting more types of graphs. Graphs is a huge world of hypergraphs, multigraphs, heterogeneous multigraphs. All the mixes you can think of are out there. And we're trying to support, the real world is a dynamic place. It changes all over time, and we're going to support dynamic graphs in GPU memory, so you can keep a graph alive and keep changing it as it morphs through time. and reducing the cost of doing these things. We'd like to fit what took us 1,000 GPUs into only 200 GPUs next year, right? That's something we're working on also. And working with database vendors. We have a project with TigerGraph right now to integrate TigerGraph as a data source tightly with cuGraph, so we can compute PageRank and these kind of features and hand it back to TigerGraph very, very quickly. We've clocked about a 200x speed up for running PageRank and Louvain on TigerGraph. But we're also working with other database vendors out there. Because we're not a database, we're just calculate analytics very quickly, and embeddings are a lot of complication to compute also. So we do these things as a service back to databases and back to machine learning packages. And I'm not doing this myself. I have a big team helping me. I like to thank my team. And that's it. Any questions?
Yeah, thank you, Joe. And we do have a question from Jeff Shaw. He says, can we use the graph in TigerGraph to train our GNN models?
Yeah, very, very, very much so. We're definitely working with TigerGraph right now to make this happen faster and easier. But it's possible today to do this. If you export a snapshot from TigerGraph, we can import that into cuGraph and train GNNs right now. Yeah.
I have a question, actually. That's a kind of a question follow-up from the other meetings. I think you mentioned that you can use the graph to train like an embedding and then fit into other machine learning frameworks, like, for example, XGBoost.
Yes.
I think also from Mingxi's early talk, and he's talking about a graph is, explainable, so you can trainable. But if you're using embeddings and passed to XGBoost, for example, are we still, explainable, traceable to like somebody say what's happening?
The embedding itself isn't it's kind of opaque, right? How did that embedding get computed? But it's a feature. You can point to that feature and say that feature is responsible for this decision. And then we know there's research ongoing to try to unpack vectors, right? Vectors are very common in machine learning these days. And there's a lot of research in how do we understand what a vector space represents. Today it's kind of opaque, but at least with XGBoost, we can point to that feature and say that's really important, or in this case, it's not that important. Yeah.
Got it. Any other questions?
Hi, this is Jeff again. I still have the question about the TigerGraph and GNN. So to be honest, we're interested about use GNN to get embedding features. But right now, our whole graph are in the TigerGraph. So do you have any suggestion how we download the data from TigerGraph and upload it to the to your package, to the cuGraph?
Yeah. I would recommend something like Parquet files, compressed files to write it out to disk. Parquet works well, or ORC. Those are kind of the two that we use a lot. There's also some binary formats that you could use. HDF5, for example. Some people like to use that one. But today we have to write it to disk in some format. Yeah.
Okay, so you mean right now we still need to download the data and to create the graph within your cuGraph package and to do the GNN, right?
Yeah, that's right.
But in the future, I remember you said you are working with the TigerGraph team to create the connection between your package and the TigerGraph.
Yes.
Do we have the timeline about it?
Well, we're trying to get this working by the end of the year. So it should be available early next year out there.
Okay, sounds good.
So Joe, we have another question. Amit says, once he load the graph into cuGraph on your on the system, and can I incrementally refresh it instead of loading it again? It says, I guess this is the dynamic graph you're talking about.
Right. So dynamic graphs are important. We're not doing that yet. Today, we just rebuild the whole graph right now. Very wasteful. I recognize the need for dynamic graphs. Again, dynamic graphs should be available probably in the second half of next year. That's when the timeline is slated for right now. So by this time next year, would have that working. So you could keep the graph alive. That's what I mean by keep the graph alive, is allow updates and allow changes without dumping the whole thing and recreating it. Yeah. But it's a whole new data structure, right? Dynamic graphs are not easy. Yeah.
Cool. Any other questions? Either you paste on chat or just unmute yourself. If not,
Yeah, I got
okay,
Yeah.
go ahead.
I got a question for you. Just hold on, let me kill this guy. So the question I have is, once you have the dynamic graph, so I'm going to incrementally, add more to it, but for different use cases. So I made enhance it for application A and enhance it more for application B. But then there is only one graph on your side. So can I filter it based on what I need for application A versus application B?
Sure.
If
Yeah.
you're a database.
We have that today. We have a predicate masking. So basically you can apply a predicate and just hide big chunks of the graph that you're not interested in. You keep it in storage, but it's not active for a given analytic or given algorithm. Yeah.
So how long do you going to keep that dynamic graph? I mean, it's a very large thing and you have to hold on to it.
Well, it depends what the application is. If you want to have real-time responses, we keep it forever, right? We keep it up 24/7. If you want to do an analytic and be done, we shut it down. Yeah, so it depends on your use case.
Yeah, so it is economical to actually for you to hold on to the entire graph because you become database effectively now.
We're getting close, right? Ideally, what we do is we link to a database, let them be the persistent store, and we only update embeddings, right? We get an update, we do a quick embedding calculation, get back a new embedding. That's more realistic, I think. But the dynamic graphs are valuable. There are users out there who want them to be running 24/7 because of real-time needs for fraud detection, for example. And it's worth running enough GPUs to do that because it's so valuable.
Yeah. So once you have the dynamic graph, then it is very important to also version the data, because I'm going to analyze it for like fraud as of or compliance, particularly as of end of last month versus as of last week. Legally these things are different.
Yeah, there's just time stamps and temporal data goes right along with dynamic, right? You have to know when this happened. When did it change?
Yeah. Every data record will have a begin time and end time. The SQL is standard effectively.
That's right. And that's part, I didn't mention it, but that goes along. In fact, we'll have the temporal aspect before we have dynamic. So we'll be able to do these time filters and time-based sampling before we can do the full dynamic graph. But they go together, right? They really do.
Yeah, wonderful. Thank you.
Yes, so several financial institutions are using temporal graph for the fraud